So I'm here to talk to you guys about outliers, but, well, you guys can ask any question. I didn't bring my bow, so you're safe for now. Ha! So, where is it? Okay. So the first question, I think, is like, what are globular clusters? Because I'm saying, I'm going to talk to you about evolved binaries and globular clusters, but I think I better tell you guys what globular clusters are. So they're actually objects that orbit around the center of our Milky Way. So all galaxies have globular clusters, but the ones that I study are from our galaxy. So we have here the bulge, the disk of the galaxy, the halo, and globular clusters, they populate this area here, and they just circulate around the center of the Milky Way. And actually, their distribution around the center of the Milky Way allowed us to determine for the first time that the sun was not close to the center of the galaxy. It was actually kind of far away from it. So the distribution of them was very important. But why do we use clusters to study stars in general, not only the evolved binaries that I'm going to show you? Well, globular clusters, they have some characteristics that would put them as, you guys remember when you studied chemistry and the teacher was teaching you about the ideal gas? And it was very sad for me when I found out that the ideal gas didn't exist. Yeah, I was like, what? When I got in college, I was like, what? Does it exist? You're teaching us lies. But yeah, so globular clusters are kind of that for stellar evolution because we treat them a little bit as simple stellar systems. Why am I doing this? Because they are not that simple, but we pretend that they are for some things. And why can we do this? Because globular clusters, they have some particular characteristics that help us analyzing the data. For example, the stars in a particular clusters, they are at about the same distance from the sun. And the most important, I think, are that they are formed, the stars from a cluster, they are formed from the same cloud. So there was a cloud, a molecular cloud that was quiet there, and something happened close to it that made it start the stellar formation in it. So all the stars in a cluster come from the same molecular cloud. And also, all the stars in a cluster, they have about the same age. So the only difference, as I'm going to show in a few minutes, is the mass. As we all know, the more massive a star is, the faster it evolves. And so that helps us determine the age of a cluster. And, well, all of the stars in there have these parameters that are kind of fixed, so that makes them the ideal gas of stellar evolution. So here I want to show you guys a few images just for you to visualize some of the clusters. So we have M4, Omega-10, M80, and this one was obtained with an Earth telescope, this image from M4. But when you go to Hubble data, it's not appearing very well, but this is the same cluster as this one, but is in the center here that it was very crowded. But when you look at with Hubble, you can separate each stars. So are things that help us look into different regions of the cluster and observe different. But you can see that they are very, very crowded. And as a matter of fact, globular clusters, they have from hundreds of thousands to millions of stars in this globe of stars here. So, okay, here I'm showing you guys an image. That's the pretty image that all astronomers show to people, like, look how astronomy is so colorful, right? I thought all that, and I was like, wow, I'm going to work with all these images. But this is still awesome. It's just that it's not that fun as I thought. So you look at this and it's like, oh my, astronomers see this stuff all colorful. No, we don't. As a matter of fact, what we do is, Okay, we go there and we use filters of colors in our telescopes. Why do we do that? Because with those filters, we manage to highlight certain stars. So, for example, here, in the blue image, we have some stars that are brighter here. We're highlighting the stars that are hotter. When we look in the red image, you see that the brightest ones are not the same here. They're different. Here we are highlighting the coolest stars in the cluster. And then to show to people and show them how beautiful the universe is, we make this colorful image. So people are like, oh, the universe, if I go to space, I'm going to see all this colorful stuff. Kind of, you know. Maybe, you know, if you have a filter in your eye. But okay, fine. But now I'm going to serious business. So, okay, back to this image. How do we get to analyze this and, wow, get the parameters from this cluster and see how old it is and, wow, how far it is? So we have this image, and the first thing that astronomers do to analyze this, let's separate them, let's sort them by temperature. So what we do is we separate from hot and cold. So now we have the hot stars here, the cold stars here, the one in between are kind of white here. But well, it's not enough yet. And then what we do is we sort them by magnitude, by their brightness. And then we do this. And there you go. There you have it. The name of this is color magnitude diagram. With color in this X here, meaning temperature. So the temperature grows and rises in this direction, so the cooler and hotter. And magnitude comes from the brightness of the star. So the brightest are here on top, and the faintest are here on the bottom. And all these things written in here, they are the different phases of evolution of stars. So the stars that are in here, they are in what we call main sequence. That's when the stars spend most of their lives. That's when they are transforming hydrogen and helium in their cores. And then when it ends, this is the main sequence turnoff. This point here tells us the age of the cluster. Help us when we have models, we fit models in there, and we get the age of the clusters mainly from this point here, because it helps us know the mass of the star that is here give us the age of the cluster, because that's the mass that's about to end their fuel inside. So after that, you go to the red giant branch, horizontal branch, where some of the stars are going that have mass high enough. They're going to start to burn helium in carbon and oxygen in their cores. And in a cluster like this, like a globular cluster, they are extremely old objects. They have from 9 to 13 giga-years. And so they don't have the more massive stars, like 10 solar masses, 100 solar masses. They already evolved long ago. Those stars you can find in open clusters, for example, that are younger, but, well, they are not as fun as globular, so I'm not going to talk about them. But they are younger, and they show the more massive ones, but I think older is cooler. You know. So after that, they basically go to the white dwarf cooling sequence that 98% of the stars are going to become white dwarfs. So most of the stars in the universe are going to cool as white dwarfs. So you see, guys, most of the stars are cool. They're going to be like cool. I'm just cooling here, cooling white dwarfs. And what does this plot do for us? This plot makes easier for us to identify the stars and get the parameters for them. So we come from something like this, that you look and see, okay, I have blue, I have red, I have yellow, and I don't know anything about it, to this that you can actually get parameters from, and you can actually study this cluster from basically the image of the cluster. So here's just to show you guys how pretty single stellar evolution is. What do I mean by single stellar evolution? A star that is like our sun, for example, is a star that is alone, like the closest star is 4 light years away, so nothing is going to disturb its evolution. So it's basically straightforward. The star has a certain mass, supermassive, it's going to become a supernova. Another one is going to become a black hole, it's going to go through supernova too. Others are going to go to neutron star. But as I said, 98% of them are going to become white dwarfs in the end. So they're going to evolve. It's really straightforward, like don't have to think about it. But when we go to binary evolution, things get a bit more complicated. And see, I told you people would think it was funny. My husband said that this was not my best joke. And I was, come on, I thought it was so cool, you know. Thank you, guys, thank you. So when you go to binary evolution, it's much harder because I didn't even go and put like the mass of the star. Like you have a binary system that's composed from 2 stars that are still like in their first phase of evolution. So basically the outcomes can be those 2 stars are binaries, like they are orbiting around each other, but they are far enough that they're going to evolve like the other one is not there. So they're just going to evolve as single stars and they're happy and all that. But there's the possibility of that those stars composing this binary system are kind of close together, or they are supermassive, and when they are not so close, but when the first one that's more massive evolves, it's going to get too close to the other one, and they're going to go through some sort of mass transfer. And that, I gave spoilers, sorry, that makes them being called the stellar exotica. Stellar exotica are binaries that went through some mass transfer during their lifetime. And some example of those, they are pretty cool, I think. My supervisor said the binaries are not cool, and I'm like, but they're awesome. They all behave like humans, you know? Because if you think, like, you can make a model of humans, like, oh, they have this average height, this average weight, and all that, but you cannot go and through a specific person and use this average model to describe it, and that's kind of what happens to binaries. My supervisor said he stopped working when he figured that out, and I'm like, too late for me. Now I have to do this, but they're fascinating. So some of the binaries that are stellar exotica are, one of them is the blue stragglers. I'm going to show their position in the color magnitude diagram that you guys know what is right now in a few seconds. Blue stragglers, they are the result of a binary system that actually merged. So those stars, they were close. It was in a binary, very close together. And what happened is when the first one evolved, it engulfed the second one that was less massive, and they spiraled it together until they actually merged. And so now it appears in a position in the color magnitude diagram where there shouldn't be any star if they did not exist. The other ones are X-ray binaries and millisecond pulsars, and also the cataclysmic variables. They all have some X-ray emission, but X-ray binaries have one of the stars in the binary system is a neutron star. The millisecond pulsars, well, one of them is a pulsar. And cataclysmic variables, one of the stars in this binary system is a white dwarf. And the neutron star and the white dwarf in this system is the one that is receiving, are the ones that are receiving the mass from. And extremely low mass white dwarfs, they're very interesting because they have been figured, like people discovered them in the galactic field about 8 years ago. And there are just 80 of them cataloged. That's a very small number. And so these stars, they are, what are extremely low mass white dwarfs, right? They are white dwarfs that have 0.3 solar masses. And with that mass, 0.3 solar masses, there's no way that through a single stellar evolution that star could get to that mass within the age of the universe. So that star must have given its mass to another star somehow within its life. So these stars can only exist if they went through a binary interaction mass transfer. And that's exactly what they are. So I started my work with this 2 years ago looking for this, and I found this and much more. And it was very complicated. So let's begin to show you guys where they show themselves to us, right? So this is a color magnitude, that's the color magnitude diagram that I work with. It's not the colorful, pretty one that you guys saw, but it's pretty cool anyway. So this is 47 Tuc, is one globular cluster that has about 11 giga-years, so it's pretty old. And this is a complete color magnitude diagram. So we have the main sequence, the red giant branch, and the white dwarf cooling sequence here is complete. In the plot that I showed you before, it was not. So here's the whole population of white dwarfs of this cluster. So first things first, I'm going to show you guys where the main sequence binaries are in the color magnitude diagram. So they populate this area here, this range, that is about 0.75 magnitudes brighter than the main sequence. Why is that? Because when we combine the flux of two stars with the same mass, and you convert that to magnitude, you get that if we observe them as one, we're going to observe that 0.75 magnitudes brighter than it, and that's the maximum. So the ones that have a lower mass and a higher mass, they're going to be in positions a bit lower than this. So this is the expected. The normal main sequence binary stars are going to be there. But let's start showing the blue stragglers. So the blue stragglers are here. There shouldn't be stars going in this direction here anymore because the main sequence turn-off is here. And there shouldn't be stars more massive than that within the age of this cluster. So they can only be here because they merged and they have this extra fuel to burn for a little longer. And so they appear here as in this position, but they eventually are going to end up and their fuel and go through the other stages of evolution. So how do people look for the other types of evolved binaries that are the millisecond pulsars, the cataclysmic variables, the X-ray binaries? Usually what people do is they get X-ray images. They look for all the sources in the X-ray, and then they go to a visual image and try to find in that certain position if there is any visual counterpart to that particular source in X-ray. And it actually works because people find it. And like all these points here in this plot are all 47 Tuc. I didn't want to mix up putting different clusters, but they're all 47 Tuc. And in this plot, they are showing the positions in the color magnitude diagram of some millisecond pulsars. And here they're showing the position of some candidates of cataclysmic variables. But doing this, they went and looked in the X-ray, they went in the image and tried to find a counterpart. And so I was like, okay, they're doing this, but have they tried to find something different? And then actually, now I'm getting to what I did, guys. Here, guys, we're looking at a color magnitude diagram in the ultraviolet. Okay, so in the ultraviolet, we are going, those filters, they're going to highlight the hottest objects in the color magnitude diagram, in this cluster. So, for example, white dwarfs, they are in a visual filter, they are very faint. But in an ultraviolet filter, they are kind of very bright. Like here you can see the white dwarf cooling sequence of 47 Tuc. But what I was looking for was like, okay, you have all these objects here in this gap that we should not have anything. Like the blue stragglers that I showed you guys. You see here the blue stragglers are extremely bright here. So I was like, okay, you just shouldn't have any star here. And I was, okay, there are stars here. And there are actually 147 stars in here. But when I look at a normal visual color magnitude diagram that I'm going to have to go through here, so many of those stars come to the main sequence here. Remember, many of those that were in the gap there in the ultraviolet colors, they come in the main sequence in visual colors. While some of them, a small number of them, will still be like here in this gap. Okay, so the first thing you can think is like, maybe they are not from the cluster, but we have some a technique that we use called proper motion, that we analyze the movement of the stars, and all the stars that move with this bulk of movement of the cluster, they belong to the cluster, while the other ones that are not, for example, right behind 47 Tug, we have the Small Magellanic Cloud. And all those dots that are circled in red here, they actually belong to the bulk of the Small Magellanic Cloud here. So we had to filter that off. And we know that the other ones that are circled in blue and yellow, they belong to the cluster, and they are in this odd position, behaving this weird way. So what I did, I was like, okay, so the ones that are always in the gap, no matter if I look in a visual color or in ultraviolet, well, I call them non-shifters. And, well, the ones that are here in this gap and go to the main sequence in visual colors, they are shifters. It was funny because I sent to a referee, and the referee answered like, I'm not familiar with this term. Shifters, and I'm like, yep, that's because I invented. And there's actually a very good number of it. And okay, so what are those stars that do not change color and are in this weird position? They're always blue, no matter if you look in ultraviolet or in a visual color. They are very likely to be the extremely low mass white dwarf stars that I started my work trying to look for. There are about 3 of them in this 147 initial number. But when I was looking for them, I found the non-shifters, and I was like, what is this? Oh my God. And I looked, and I couldn't find information until I finally did. And they are very likely. There's one paper from 1998 talking about them. And I had to Google it. It was pretty hard. I found on a search for Google images. It was so funny. And so these that shift, they are very likely composed by one star that is in the main sequence, a red star, and one star that is a white dwarf, a blue star. So when we look at them in the ultraviolet colors, we see a combination of colors of the white dwarf and the main sequence one. And then we see those sources here in this gap. But when we look at them in visual colors, those sources appear in the main sequence because the main sequence star is much larger than a white dwarf, and it is redder, and we are trying to highlight the red objects with a visual color. And so we only see the red one. And those are what I, again, call outliers. So they behave in a way that's not the expected according to the normal stellar evolution. They go out, they think outside the box. And for this, I thank you.
Thank you, Double Trouble. We're going to have some time for questions, so get close to the mic. There's a Twitter question. How rare are trinary star systems?
They are pretty rare, actually, but I don't have a number. And actually, going into binary questions, one thing that's very interesting, and I don't know if you guys ever thought about it, is those two neutron stars that, well, gave us the first observation of the gravitational waves. It's hard to have one neutron star, but having two, and what forms them? Well, they form and they first explode as a supernova, and it's a very hard shock, and if they had another companion, it's gonna just pull it away. So it's extremely rare to have three binary systems, but it's not as rare, I think, as having binary systems of neutron stars.
So last question with a hat.
There were a lot of stars in that range that were not supposed to be there.
Mm-hmm.
Do we know why they're not supposed to be there, or is this a totally new area of astronomy that you and your supervisor?
Yeah, like right now, the way that we are doing is actually the first time that it was done. What those sources are, they're likely these binary systems composed of two different stars of different colors. And so they show themselves behaving this weird way. But for now, the paper has been just submitted. I just finished this. And we have some ideas of what they might be. But as every astronomer knows, all we need is we just need more data. That's all we need. Like HST data is, yeah, that's it. Yeah.
So with that, let's thank Double Trouble again.
Thank you.